This is day 2 of Unit 5. We started today with a warm-up. So pause the video, try it, and then play to check your answers. So the first question says to write in standard form, state the degree and classify by degree and number of terms. So I'm going to go ahead and multiply the two binomials together first. Let's put this down here. So when I do that, I'm getting x squared plus x minus 12. And then I'm going to distribute the 2x, and I'm going to remember my y equals in the front of that. So 2x times x squared is 2x cubed. 2x times x is 2x squared. And 2x times negative 12 is negative 24x. So now I have my equation in standard form. The degree is the highest exponent, which is 3. And because it's degree 3, it's cubic. And because there are 3 terms, it's a trinomial. So this is a cubic trinomial. Number 2, find all of the zeros. Well, first I'm going to substitute 0 in for y because I'm looking for the x part of the x-intercepts. Then I'm going to factor that. So that's x squared minus 9 and x squared minus 4, which factors further into x plus 3 and x minus 3. So my solutions are plus or minus 3, plus or minus 2. Those are the zeros. Number 3, simplify. So I'm going to take the square root of 2 squared plus negative 6 squared, because that's how we find the absolute value of a complex number. So that's the square root of 4 plus 36, which is the square root of 40, which simplifies to 2 root 10. So 2 root 10 is the absolute value of 2 minus 6i. Okay, that takes care of the warm-up. Today, our notes were in both the packet and also in your notebook. So we started in the packet on page 3. So on page 3, it first asks you to graph y equals x cubed. So to do that, we did a table, and we just did negative 1, 0, and 1. So when I cube negative 1, I'm getting negative 1. When I cube 0, I'm getting 0. And when I cube 1, I'm getting 1. So negative 1, negative 1. I'm going to plot that 0, 0, and 1, 1. And I can go ahead and graph my cubic, which has a point at 0, 0, which if you think back when we graphed y equals x squared, that was a parabola with a vertex at 0, 0. And remember, 0, 0 was really important because it helped us to locate the graph, how it had been shifted or translated. Cubic is the same way, except for 0, 0 is not the vertex. It's called the point of inflection. And it's called the point of inflection because it's the point where the graph changes what we call concavity. That's a term you probably heard in science. So from that point of inflection, it's concave up to the right of the point of inflection, and then it changes concavity and goes to concave down at that point of inflection. So that's why it's called the point of inflection. So we're going to label that point of inflection 0, 0 because that's an important point. Okay, so then the next thing it asks you to do is to graph y equals negative x cubed. So we know from our experience with parabolas that we're just going to take our graph and reflect it across the x-axis. So think about that. If I reflect this graph across the x-axis, I'm going to change pen color here. Then this point here, which is currently at 1, 1, is now going to be down here at 1, negative 1. And this point, which is at negative 1, negative 1, is now going to be up here at negative 1, 1. And so now the concavity is flipped as well. So it's concave down on the right and concave up on the left. So that graph is y equals negative x cubed. And the other graph is the normal y equals x cubed. Okay. So then the next thing it asks you to do on page 3, part 3a, it asks you to figure out what a graph of a cubic would look like if it had been vertically stretched. And then B is vertically compressed. So think about that. It's just like a parabola. If I grab the ends and stretch vertically, the cubic's going to look skinnier. And if I push up and down on the ends to compress the graph, it's going to appear wider. So add those two graphs to your graph. So I'm going to make first a vertically stretched graph. So it still has that same point of inflection, but vertically stretched, it's going to be skinnier or closer to the y-axis. Okay, and then a vertically compressed cubic, again, is still going to have that same point of inflection, but is going to be vertically compressed, so it's going to appear wider. That's our vertically compressed graph. So then equations, the one that I just graphed, in part B, it asks for an example of the equation. So that would be something like 1/4 x cubed equals y, let's say. And an example in 3a of an equation for a vertically stretched graph would be something like y equals 3x cubed. Okay, so again, just like the quadratic equations, the a value is greater than 1 for a vertical stretch and less than 1, and of course we're talking about the absolute value of the a, less than 1 if the graph is vertically compressed. Okay, so that takes care of the most of page 3. And then there's also a part 4. Let me go back to my normal pen color here. So there's also a part 4. And that asks for the general equation. Well, we know for a quadratic, it's our vertex form. So if I adjust that just slightly, because remember that vertex form is when hk is the vertex. So it's allowing for the translations and the transformations. Well, we've just discovered that the cubic translations and transformations are the same. So it's going to look very similar, but it'll be cubed instead of squared. And hk is no longer the vertex, it's the point of inflection. Okay, so that takes care of our notes on page 3. So the next thing we did, these are just going in your notebook. I asked students to copy that equation and make yourself a coordinate plane, and then we're going to graph that. So we know that the shifts are the same, so +4 would be left 4, and -2 would be down 2, which means the point of inflection, I sometimes abbreviate that POI, would be -4, -2. So I'm going to go ahead and plot that on my graph. Now, I also look at the a value and I see that it's 1, which means this graph has not been vertically stretched or compressed. So when you have a cubic that has not been stretched or compressed, I'm going to go back to our previous graphs, it's going to look like the most basic one, the one in purple here. So from that point of inflection, over 1 and up 1, and left 1 and down 1, so over to the right 1 and up 1, left 1 and down 1, that's what the most basic cubic will look like always. So if it has not been vertically stretched or compressed, which this one has not, then from that point of inflection, just right 1 and up 1, and left 1 and down 1. and then concave up on the right, change concavity, concave down on the left, and then just label your point of inflection. Okay, so that's what our graph looks like. The next example. So hopefully you realize by looking at this next equation that the point of inflection is the same. Okay, so I'll just highlight that point of inflection. But I see that I have a 1/4, so I know the graph has been vertically compressed, which means it's going to be wider. But I can't just freehand it. I don't know how wide to make it, so I have to find some other points. So what we'll do to find some other points, we will make a table. We'll go ahead and put the point of inflection that we know. And then I really just need 2 other points. My suggestion to get the other 2 points would be to go one to the right of the point of inflection and one to the left, which would take us to -5 and to -3. So I'm going to go ahead and substitute into my equation -5 and also -3. So if I put in -5 plus 4, that's -1. -1 cubed is -1. -1 times 1/4 is -1/4. And -1/4 minus 2 is -2 1/4. Next, -3. -3 plus 4 is 1. 1 cubed is 1. 1 times 1/4 is 1/4. And 1/4 minus 2 is -1 3/4. So let me plot those now. So -5, -2 1/4. -5, -2 1/4. So just a little bit below -2. And then -3, -1 3/4. -3, -1, and almost -2. Oops, right there. So we can see that with our point of inflection going concave up to that point, through the point of inflection and going concave down, it's definitely wider. So that's our 1/4. Okay, so that's what that graph looks like. Okay, next. There we go. So go ahead and pause the video. Try this one on your own. You're going to graph the point of inflection first and then 2 other points, and then you'll have your graph. Okay, so I can see that -3 is right 3 and +1 is up 1. So I know the point of inflection is 3, 1. So I'm going to plot that 3, 1 right there. So I can see -2, which means I am going to have to get 2 other points because it'll be vertically stretched, and I see negative, so negative orientation. So I'm going to go 1 to the right of 3, which is 4, and 1 to the left of 3, which is 2, and substitute in. So 4 minus 3 is 1, cubed is 1, 1 times -2, -2, -2 plus 1 is -1. Substituting in 2, 2 minus 3 is -1, -1 cubed is -1, -1 times -2 is +2, and 2 plus 1 is 3. So let me plot those points. So 4, -1, 4, -1 right there, and 2, 3, 2, 3 right there. So I can see it does look a little bit skinnier, and it definitely has a negative orientation. So I know I'm coming through this point into my point of inflection. It's changing concavity, and it's going down. I don't know why we got that extra little lump there, but there we go, to our point of inflection and concave up from there. So our point of inflection is 3, 1, and there's our cubic graph. Okay, next. So in this one, I gave you the graph. So go ahead and add that graph to your notes. And you're going to figure out what the point of inflection is and then figure out the equation. So I can see, looks like 5, -3. And I'm going to check the values to the right and to the left of that. So I see over 1 to the right and up, left 1 and down, which tells me that there is no stretch or compression factor. So I can just write the equation without with an a value of just 1. So to the right means -5, and that's cubed, of course, and then down means -3. That is my equation. Next, same idea. This time I just gave you the point though. It does not give you a second point. So realize that means that we can assume the a value is again just 1. We would be given another point if and told to find the exact equation if the graph had been vertically stretched or compressed. So just x subtracting -4 gives me +4, the quantity cubed, and then +7. That's the equation for our cubic. Now keep in mind, and we'll do some of these later in the unit, but if we were given another point, then I would be putting an a in the front. And then I would take the point that I was given and substitute in for x and for y, solve for a, and then substitute that a value back in, just like we did in the previous unit with quadratic equations. But because we weren't given a second point, then we don't have to do that step. We just write the equation with a value being 1. Homework for tonight is pages 4 and 5 in your Unit 5 packet. Do those for tomorrow. Stay on top of assignments. Don't fall behind. Remember, if you're contributing to the angel tree, you have till next week, Wednesday. So go ahead and do those tonight.